Okay, good morning, everyone. Welcome to the Climate and Energy College, and thanks for coming along this morning. Before we get started, I'd just like to pay our respects to the Wurundjeri people and their elders past and present, and any elders that may be with us in the audience this morning. Any of you that are not blind or deaf will probably be aware that we're having a god-awful debate about energy policy on the national stage at the moment. This is the National Energy Guarantee. There's with new convolutions and conniptions every day at the moment. We may get a chance to talk about that to some extent in the question time later on, but in the meantime, we've got a fantastic presentation from Kate Summers here now. Kate has been in the power system forever, without wanting to be disrespectful. You know, she was around well before the start of the actual national energy market and the various versions that's gone through. She was part of the State Electricity Commission of Victoria, then VicPool, which then became evolved into the national energy market, and then I think has experience at the precursor to AEMO, NEMCO, and then also Pacific Hydro for the last 14 years.
14 years.
Anyway, Kate is an absolute wealth of knowledge on certainly the technical aspects around integrating renewable energy into the power system, and we're very lucky to have her with us today to talk through some of these issues and the implications for our system and our market design and what this means for the future. Thanks.
Thank you. And I'm assuming that this is on and everyone can hear me. Good. Okay. Thank you very much for having me to talk. I'm just letting everybody know I am on annual leave, hence why I'm still in my motorcycle gear. And I should actually be skiing, but here I am. Just because Malta asked me to. So that's... and as a skier, of course, I am committed to seeing that we maintain snow on our Alps. It's very important. We love it. And it's actually part of the reason why I do what I do in renewable energy. Just prior to this talk, I was pulling up my favourite old textbook, which is Elgird Energy Systems. It's a McGraw-Hill publication, and I love to quote from it because the first couple of chapters are extremely good, and it's a very good book if you want mechanical analogies. And the opening introduction has this quote from Walter J. Hickel, who was giving a speech to the Stevens Institute of Technology in the US in May 1970. And it says to the students, "Your task is nothing less than to create a whole new civilized industrial technology to replace the brute machine that raised so much ecological hell." And here we are in 2018, and we are still trying to actually achieve what was the aim to the energy systems students in 1970. So I often look at what we're doing in our power system, and I know that in the NEG and all these discussions about dispatchable energy and how we love to have economics and policy basically take the primary role in terms of deciding how we're going to fix the problem. But what we're dealing with is a fundamental engineering problem. It's a fundamental engineering control problem, and it's a complex engineering control problem. And we have to examine what it is we're trying to do. And in doing that, I picked up another little quote for you, which comes out of, I think it's that one. Wake up. It's gone to sleep. Which comes out of, actually it's quoted by Simon Winchester in his book Exactly on Precision Engineering. And it's actually a quote from Bertolt Brecht, and it says, "The aim of science is not to open the door to infinite wisdom, but to set a limit to infinite error." Now, when we think about that, what we're trying to do in the power system is control a very large, complex machine. And that complex machine only works when we have coherent response from the collective of all the control systems on all the individual machines within that power system. And the issue that we're dealing with right now is that we seem to have lost our control philosophy And we don't really know what our control philosophy is. And we have people who are setting direction and rules and policy without understanding what the ultimate philosophy is, other than to have a market. And here is the fundamental problem that we're dealing with. So, what is it that sets up a reliable power system? What do we really need? And when we think about this, there are three fundamentals to a good power system: constant voltage, constant frequency, and high reliability. They're fundamentals. And what is it that controls frequency? We control frequency through the control of active power. Active power is energy. That's what we sell, that's what we meter, that's what we pay for. It's the control of active power. And every single electrical engineer should understand this from 101. Engineering 101, rotating machines. Control of voltage is control of reactive power. If we lose our understanding of what active energy does to the power system, and we think that we can control the energy dispatch in ignorance of frequency control, we have lost the plot. So in 2001, when we set up a frequency control ancillary service market, did we actually understand what that was doing to the control of frequency? And let's examine what the frequency control ancillary service market is and is not, and try to get a clear understanding of what it's actually doing to the power system, so we can understand what it is that we want to do when we transition and put new stuff into the power system. So if we go back a little while, in 2015, we saw this event in South Australia where we had a separation event and the power system dropped straight through into under-frequency load shedding. Sorry, I'm looking at this one and you're looking at that one. And here we can see that it should highlight. It's not going to highlight. Okay, so here we can see in blue the output of two very large generators in South Australia following a separation event. And the red trace is the actual frequency. And the double red line is 50 hertz. That's where we should be controlling to. When you have a separation event, it dropped down into under frequency load shedding. And the frequency was recovered. And the frequency was recovered straight away, back up to 50. Following that, we had a number of interventions from some diesel machines which pushed the frequency around. But at this point here, two large machines in an islanded area decided that they were going to provide ancillary services. And they drove the frequency from the boundary, this isn't really working, I don't think, from the boundary of 49.85 straight through to, you can see, nearly 50.6 at the top of the chart. Now, that is a control system that really doesn't know what it's doing. Furthermore, if we go to the 10th of February in 2017, get control of this, we can see this is when New South Wales was under stress. We had high temperatures in New South Wales. We had overloaded interconnectors between Queensland and Victoria into New South Wales. We had no frequency control services enabled within South Australia. And added to that, what we also had was the loss of a gas turbine. I'm going to try again to see if this will highlight. It was working before. No, okay. So as the frequency lowers, maybe that machine needs to be, so it can talk to me. The receiver's not working. Okay, so when the frequency, you can see in red that we've got the boundaries of the normal operating bands are actually in dotted lines with 50 marked in the middle. And the red trace in this plot is frequency. You can see that the actual megawatts dropped down below the boundary of what we'll call the normal operating band. So there's a normal operating band around 50 hertz, and you can see that the trace dropped outside it. And then the active power on the large scheduled generators, which is the top plot, is oscillating with a 24-second oscillation for 7.5 minutes before they figure out somewhere over here how to get the frequency back into the normal operating band. Now, the scheduled generators are the synchronous generators. This is what we call base load. This is what traditionally we control the power system with. This is the sum of all of the coal-fired power stations, the hydro power stations, and also some gas turbines if they're operating, right? This is the synchronous machine fleet. Traditionally, we always had good control of these machines. In fact, we know how to control them, but at this point in time, we're not. And when people talk about the intermittency of renewable energy, let's have a look at the next two charts. Semi-scheduled generation and non-scheduled generation is the sum of all the wind farms, all the solar farms, and maybe a few little synchronous generators like my hydros up in northern Victoria, which are about 4 megawatts each, right? So this is a total here of about 650 megawatts. And down here, this is a, oh yeah, okay, thanks. This is a total, got a tent pole now. Right, this is a total of just around 300 megawatts. This total up here is sitting at 33.4 gigawatts, right? So this chart is in gigawatts. So this is hundreds of megawatts because it's 0.65, and this one is 33.5 gigawatts. I know it's a little bit hard to read, but we will publish these slides. Is this intermittent? No. So where does the myth of intermittency come from, other than the fact that we think about it from the point of view of whether we know it's going to be there today, tomorrow, or the next day? Isn't that problem more a problem about forecasting? Because in this instance, this is acting like base load, and this is misbehaving. Now, these guys are being paid to control the red line. They're being paid hundreds of millions of dollars to control the red line. These guys are paying these blokes to control the red line. Now, why does intermittent generation actually not respond to frequency? And it's because it's asynchronous, or it's connected through digital control or through inverters. So it can tolerate wide movement in frequency because it's not directly coupled to the frequency. But these guys, when the frequency goes all over the show, we are changing the fundamental understanding of how we control and study synchronous machinery, right? Because what's happening in the electromagnetic flux within those machines, it's going all over the place. Now, in engineering, we contemplate constant flux models because we know if we control the frequency, we are controlling the flux. We have a standard model. We can apply that standard model. In Australia, as a result of our market, we've basically thrown that out the door, said, market knows better. We can drive our power system like this. And I can tell you one thing about electrical equipment. It is really good for about 4 or 5 years. You can misbehave for about 4 or 5 years within certain tolerances. And after that, it becomes highly unreliable. And you start to see failures, and you're scratching your head as to why you're seeing failures. Now, that also goes for lots of other equipment in the system, like transformers and any other rotating machinery that seems to be connected to it. Because we will get abnormal heating conditions occurring in those machines. We're already starting to see machines getting sent over to Germany to get rewound, or to Japan or something like that. So having given you that little chat, let's have a little look at what a specialist would say about the control. Back. This is what a specialist would say about what that control system looks like. This is a limit cycle of the kind observed in any dynamic system in which deadbands and gains are established without real understanding of the dynamics under control. This is pretty sad because in my lifetime or in my career, I know that we knew how to control this. And what we're watching is the deterioration of good engineering practice while we work our way through a market system that has basically altered the groundwork. So let's have a little look at the frequency distribution. I think many of you will have seen this chart. It's been published by the AEMC without reference to Pacific Hydro. But we put together this chart from 2001 when the reliability panel was contemplating changing the frequency standards when they introduced the frequency control ancillary service market. And this is what the frequency histogram looked like in 2001. Now, if you examine a histogram, where the shoulders are, it tells you where your primary control commences, right? And when you have that, you're seeing primary control actually active. When you're seeing this, you're seeing a version of, well, there is some control there, but it's sort of a long way out. So this is our new frequency standard. Anywhere between here to here, we say it's okay for the power system to operate. That's our normal operating frequency band. Originally, our frequency band was 49.5 to 50 point, 49.1 to 50, 49.9 to 50.1 was the original band, but we had mandatory governor deadbands or mandatory governor response kicking in, and the largest deadband that you could have was plus minus 0.05, I think. So that would be consistent with that, right? It's documented in one of the papers that I put out in 2016. We charted what that looks like across, we did this heat grab. Now this one is a little bit out of date. We have charted 2017-18 and there has been a small improvement. Maybe because I've been raising a few eyebrows and talking to people about what's going wrong. But you can see 2012, 2014, we still had control. We still had fairly reasonable primary response. So what has happened from here onward that it's let go? Now people might say, oh, well, we've got so much renewable energy, it's making the problem. But let's go back to that other chart. Was renewable energy affecting the frequency? No, it was acting like baseload, remember? It was more stable than the large synchronous fleet. If anything, it has a stabilizing effect because it's not responding to the oscillations in the power system. And so when we're sitting in here, what's happened? Well, we can point to a couple of things. We can say that the large generators in New South Wales got privatised. So AGL and Origin basically took them over, along with, I can't remember if Alinta got one of them or two of them. And the end result is we have also had an evolution in control systems. And what we have now are digital controllers that enable generators to respond to external signals. So we have unit control that will tell a generator to respond to its market signal because the market tells it. And of course, the rules say you must follow your dispatch target in a linear fashion from A to B across that 5 minutes, because that's how we assume it's all going to work, right? So they're following them and ignoring their governors. Now, what's the governor do on a synchronous machine? It maintains its rotational speed to its nominal, to close to its nominal rotational speed. That's what synchronism means. We set a nominal rotational speed and all synchronous machines should be behaving such that they maintain synchronous speed. But what we've done under our frequency control market is we've allowed them to have a much wider tolerance around 50 hertz. It's a little bit like allowing your cruise control on your car to have a wide response. Now imagine how frustrating it would be if you set your cruise control to 100 kilometers per hour and you're zooming along the Hume and you start going up the Great Divide or whatever, and it starts to slow down. And your car does not decide to accelerate until it hits 90 kilometers per hour. And then you go over the hill and you go down the other side and your car speeds up to 110 and it doesn't decide to decelerate until it gets back, you know, like until it hits the flat or something, right? Or even then, it won't even know where 100 kilometers per hour is. But that's the type of control system we have now set on the eastern seaboard. It's a fundamentally problematic position to be in. So let's have a little look at what it used to look like. So in 2003, the synchronous machines, of course, we don't have any renewable energy really. Oh, Pac Hydro had a couple, right? A few wind farms and things, but as we saw, the wind farms were behaving themselves, weren't they? So here we are. This is 50. I'm sorry about this chart. It is a snapshot out of an archived network event, which I can provide to anybody if they want to read it. But we separated not long after Queensland had interconnected. This was a separation event between New South Wales and Queensland, and clearly Queensland was exporting into New South Wales. And here's 50. And this is 50.05 and this is 49.95. And here we are sitting there, separation event occurs, overgeneration in Queensland, high frequency, takes a few minutes, it's about 10 or 12 minutes to get back to here, and it takes a fair while to wrap back up here. But look at where it comes back to. And then resynchronism was over here. So it took a while to resynchronize. I think they had issues with trying to find where to get the actual resynchronism. But you can see we still have reasonably tight control. It's quite different to what we're experiencing now. So if we have a little look at what we've done to our control philosophy. Before the NEM, we had multiple areas of control in which we applied the AGC system, which means it's a control system that controls the areas, right? After we created the NEM, we decided that we could control the whole of the eastern seaboard as one interconnected region. And the way that we would control our interconnector flow, instead of using a real-time control system, well, when I say real-time, a SCADA-based control system, which is a second-order control system, to manage the flows on each of the interconnection between each of the natural regions within our system, we set it up so that we would have one large area of control, and we also set it up so that we would manage those interconnector flows through the energy-constrained dispatch. And we said we can do that. Why? Because we've got control of frequency. If you've got control of frequency, you have tight control of your active power. If you have loose control of your frequency, you have limited ability to actually manage your active power flows. And I'll demonstrate that later. Before the market started, we had mandatory governor control with tight deadbands on the governors of the synchronous machines. And that enabled all the synchronous machines to operate to within a very close tolerance of their nominal rotational speed of their shafts. And what we have done by saying that your governor control, it's not mandatory, but you can offer us a service under the frequency control to actually provide frequency control. Now, let's think, what are when we think about ancillary services, and I don't have a slide on this, and I'm sure that people have heard FCAS, let's think about what those services really are. So people would be aware that we have an energy market, and then we have 8 frequency control ancillary services, which are also a market. 6 of those services are contingency response services, So there's 3 raise services and 3 lower services, and they are 6-second, 60-second and 5-minute services for the provision of spinning reserve. That's what that does. Contingency services are a payment to people to back out of the energy market, to provide the headroom to raise if we lose a generator. And the lower services are that a generator nominates that they will back off if a large load trips off, like a pot line. That is reserve service. That's all it is. The other 2 services are the AGC, or what we call regulation services. Now, regulation services are a second order control system. They are operated out of the centralised SCADA system from the control rooms, and they are plagued with time delays which occur as a result of communication time delays. Now, electricity travels at the speed of light, right, or approximately. It's pretty quick. We know that when South Australia went black, it went black pretty bloody quick, right? There is no human intervention that you can do if a power system decides that everything's gone to hell, right? Nothing you can do. It is incumbent on the engineering of the power system to ensure that there are protective systems which manage how we control that power. But what we've done is we've set a cruise control system, quite legal, and actually backed up by the lawyers who are now scratching their head as to how to fix it, because if anybody read the Frequency Control Ancillary Services Review, 250 pages, I didn't find anything that was going to fix it. You would know that we've set our cruise control at such a point, it's not going to do anything until, well, the under frequency load shed kicks in, so all your customers are off, or, you know, basically, what's another analogy for it? Well, if you're driving up a hill and you don't put your foot on the accelerator until you're 2/3 up the hill, do you ever recover the speed that you were doing at the bottom? No, you don't. So having wide settings on these generators and allowing the rotational speed to slow down and contribute their kinetic energy to the power system, inertia, but not support it with with mechanical power back into those generators to keep them rotating, we can't save the system, because generally they will slow down and keep slowing down because we haven't put any arresting energy back into the system to bring them back up to speed or to keep them at speed. And it takes time to get the energy into those machines to make them do something. So the wider the setting and the later they commence, the less reliable our power system is. And just to sort of illustrate, this is back on the event on the 10th of February, just to illustrate how problematic this is. This is just highlighting some of the oscillations that you see. And this was one particular unit that we're actually looking at here. And just to show you that what happens when the dispatch target comes in. So here's the system event happening. Here's the oscillation. This is on a particular large hydro machine. This is an aggregation of the power station. When the dispatch target comes in and it's going to here, notice that the oscillations grow. And why? And that is because the units themselves want to respond to this physically, because that's what they're coupled to. But this is what its control system is telling it to do, because the market says so. So it's going down here to where the market says so. The frequency has not recovered, but it is reducing its active power. So if you have low frequency, what do you need to do to your active power? You need to increase it. But here's the market telling it to go counter to what, because the market doesn't know what the frequency is doing. The market does not know what the frequency is doing. It's only every 5 minutes, right? Frequency is every moment. where am I going to now? Okay, so just to follow up, that oscillation was translated into Tasmania because Tasmania is connected through Basslink, and Basslink is responsive to frequency because it transfers services. And it amplifies it into Tasmania, so the poor little hydros down there are responding to that oscillation. This is a really good way to bend a shaft, except that this is 24 seconds. It's not an electromechanical oscillation. But it's still very much wearing these units out faster than we need to. Okay? So just to see, have we fixed the problem? So this is the next event, which happened 5th of June 2018, and we decided that we'd just have a little quick look at what was going on. And again, blue is active power and red is frequency here. Oh, notice that other chart was the other way around, but sorry. And here we are, non-scheduled generation and semi-scheduled generation, those naughty intermittent machines. Again, and why is it that they do not respond or they're not intermittent? They're not intermittent because when you put varying sources together and you collate them, you actually get a smoothing effect. Now we know this. So intermittency, as it has been propagated in many, many conversations in every single policy document, comes from the study of microgrids or individual solar panel output or individual wind turbine output. But when you put a wind farm together and then you put more wind farms together and then you put more solar farms together, this is the output you get. If these start to participate in the frequency control market, what will they do? They will start to look like that, right? Because the market itself is a little bit flawed. Just a little bit flawed because it's not primary control. It is reserve service and it is the second order time error correction services. Time error correction services cannot control frequency. We need to control frequency in the primary sense on these fellas, because if they don't do it, nothing a little 2 megawatt machine down here does will fix what the 33 gigawatts or 22 gigawatts or whatever is doing. It can't physically fix it. And batteries can only do a little bit. They're good, but we need to fix that before they break themselves. And then we can integrate our batteries comfortably and we know what we're dealing with. We would know exactly how many cycles we would have if we put a tight frequency band on things. And we'd put a proper droop system in place so that it would actually control. I would happily put droop on my wind farm if these guys were behaving themselves. P-mech must equal P-elec. It's as simple as that. The power in and the power out on a synchronous machine needs to be balanced. Now, we talk about the system, but we've forgotten about it on the individual machines. So we've undermined our entire study of how we actually study the power system for response to contingencies. How am I going on time there? Good? Ah, perfect. Okay, so 5th of June. Oh, 7th of June. Here's another one. 2 days later. And here we go. I think this was the loss of Cogan Creek up in Queensland, which is the largest synchronous machine on the power system. We dropped down to 49.7, 49.6. We take forever to get back into the normal operating band. And then when we do get back, we go straight through 50 and up to the other side of it. Because we don't really know where 50 is anymore. So what are our primary control issues? We know that primary control has been removed from the normal operating band, and we know that AGC, or the regulation services under the FCAS market, are actually trying to control the frequency. It can't, because it's a second order control system. Now, I'm just going to ask an internet question here, because I'm sure I've got a few geeks in the audience. How many people get frustrated with the current performance of our internet? Yes! I don't know, I'm listening to Fran Kelly in the morning on the digital download on the radio, and it suddenly goes, hello, the news is... And you pick up half a sentence later or whatever, right? So that gap is pretty annoying, isn't it? Now, if we send a dispatch target out of the market systems through the 4G network, because that's what a lot of generators are doing, and it comes out of the market systems, it's got to go to your central database, it's got to then get passed, it gets sent out through the internet and down into your SCADA systems at your wind farm. I say that the market dispatch is subject to whether or not the local farmer is downloading something on Netflix. Is this the way we should control our power system? Now, we have laws that say that you will receive your dispatch target via the MMS system. And AEMO interpret that as meaning you'll get it the way we're sending it to you. By the way, that's file transfer out through the internet, CSV. You've got to do something with it and get it to your site. Now, that is, as far as I'm concerned, a second-rate, inadequate communication system for the control of the Eastern Seaboard infrastructure. Doing things through the internet is not as reliable as doing things with primary control, which is actually at your location. You should have a signal at your connection point that you measure and you respond to, because everything should be done through that local control, because nothing coming over the internet can save us when the poo hits the fan, right? So my analogy to this is what we have done to our power system is we have gone from centralized planning, which of course all the economists can't have centralized planning with distributed control. And what we are doing, and you can see this in every single policy document that's coming out and everything that is saying we want more and more information, we want more and more control of you. We even want to control the solar panels on the roof of your house, right? What this means is we're going from centralized planning and distributed control to distributed planning and centralized control. Centralized control will not manage control of the power system. But this is underlying all the market thinking, that everything can be done from a central point and a signal comes out to you and you will respond to it. None of that will save the power system when it all goes wrong, because it happens in the blink of an eye. And in milliseconds, machines and controllers and other things should be responding. Now, a synchronous machine response, when it has a properly tuned governor, takes about a second to start doing something. That's the time it takes for a machine to sense what's going wrong and send signals to its actuators to open the big steam valves and get more steam into its turbine. So we always say the first second of an event, approximately, is an uncontrolled thing. But then we expect the control systems to kick in and do something. But if those control systems go, yeah, we know the frequency's going. Okay, I'll do something now. It's too late. So, where am I going with all of this? Right, so what we're seeing is that the market control actions return the generators to a dispatch target despite the frequency. They follow the AGC, which is the FCAS regulation targets, over their primary governor control. So if the AGC, which is a 15-second time delayed signal, says go down, even though the governor is trying to go up, they will go down because the market says so. And return the dispatch target at the end. They'll go back to their dispatch target when they're finished giving their service. So they'll only give the service that they were enabled for in the market, because that's what they're getting paid for, and then they go back to their dispatch target. Now, technically, when we study a power system, we always expect the machines to establish a new steady state equilibrium after an event. But if we force a market signal in there, We don't model it, we don't study it, but it's happening. So is the power system actually stable at that point in time? Do we know where it's going to? Because in the post-transient period, we're getting control action coming because of what the market is doing to machines. Just to highlight what this looks like in terms of system security. This is a chart from the System Black report, and I'll just run through this quickly, and I would recommend that people have a read of a paper, which I've referenced at the end of this. In this, the target for control was 600 megawatts, and this is the Hayward interconnector, and this is the actual megawatt flows. This means that if you go over the red line, you're actually insecure. And if you stay down here, you're secure. But as you can see here, you're trying to maintain a 580. They're actually trying to stay at 580, not 600. And here you can see in this box, it's 2.5% of the time they're well over the secure limit. And not only that, it's a total of 31% of the time that they're actually outside of the limit. This is not secure operation of the power system. So if you think about critical clearing time, trying to save the power system, overloads, blah, 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 this is what the actual control systems are doing. So if you lose control of frequency and you don't have tight control of frequency, the question is, does the security constrained dispatch actually work? And I would say no. Once you've let go of frequency, even though people think, oh, why do we need it? Even if you've let go of frequency, you no longer can control your active power accurately. And we did some work on this. Now this has been up, we've got an updated chart on this, and I didn't get the chance to get this in here, but it is in a later paper that's coming out in the IET, hopefully later in the year. This is the interconnector error to its target. So this basically shows that you're getting accumulated error up to 6% of the time of at least 20, well, about 5.8% of the time to 20 megawatts in 2015. And there was a period here where Basslink was in and out. And I think the 2015 period shows the worst case. But you can see it sort of varies a little bit. AEMO have done some work to fix this, but I think there's a lot of research work that needs to be done on how they're going about fixing that. And I might just leave it at that, and people can ask me questions on it more later. So our observations, that the market framework has been reverse engineered onto unit control. There's regulatory barriers that exist to good frequency control. Thank you. There's a lack of primary control, which increases our dispatch error, and our security constrained dispatch is at risk. And the FCAS, or the FCAS services that we have, are only small error control and reserve services. They are not primary frequency control, because when we created that market, we assumed that synchronous machines would maintain their governor control. So our conclusions are the primary control is essential to reliable operation. Tight frequency control underpins the accuracy of the 5-minute forward market dispatch. Dispatching frequency services changes the frequency response, and this has been proven. AEMO recently did a test down in Tasmania. We can't publish the results, but they did find when they put the governors in, they had very good frequency control. When they took the governors out, they had very bad frequency control. They analysed the effect of the 5-minute dispatch, and they did find that the 5-minute dispatch actually causes an increase in the frequency error. So this means we have an energy market that is causing costs in the frequency control market, while we are blaming renewable energy and loads. So a lot of people say, oh, it's the loads doing it. But by definition, the loads always equal the sum of the generation. And the loads have to take what they get. And if they're getting sped up and slowed down as a result of the frequency changing, they don't even know it. There's detrimental market control action, and it can occur after the system modelling time frame. So when we model a system and we look at it, it's usually about 10 seconds to 15 seconds. And the market systems can kick in after that period. And we're seeing increased costs. People are crying out for more FCAS services, but the more FCAS service we deliver, the less frequency control we have. This is indicative of a failed market. We need to get the fundamentals right. And I've got a couple of references there for you. There you go.
Okay, great. No, thanks for that great, very interesting presentation. I've certainly got a few questions, but I'll throw them over to the audience to start with. Is there any questions?
Hi there, great presentation, thank you. It sounds like these oscillations are causing extra wear and tear on the spinning machines.
Correct.
Would it not be incumbent upon the large generators to try and fix this as soon as possible because it's costing them money?
Yes, I've been in a number of forums, and I think often the influences on the wear and tear that is occurring is quite a subtle one. I was actually going to include a slide of a picture of what that looks like on a machine winding. I think the people who participate in some of the regulatory forums, generally the market regulatory people, they perhaps don't always understand the deeper, more complex areas where the wear and tear is occurring. And the engineers, they understand what's going on, and some of the operators too. We've got circumstances where some of the large synchronous machines are actually worried about stalling or losing a machine during the morning pickup, which happens at 7 a.m. in the morning, and has happened since Cocky was an egg. So every day at 7 a.m. we have a morning pickup. Now imagine, we've known how to manage the morning pickup for years, but we're now in the environment where some of the operators are worried because they're coming off technical minimums that they don't believe that they'll actually be able to respond and pick up as a result of the poor control. So I think there's an argument they think that by putting their governors in, it'll be more expensive. I think actually it's the contrary. I think you get small movement and you get a little bit of wear from the small movement, but what we're seeing here, every 24 seconds, whenever you get an event, you're getting that oscillatory behavior. And then over the minutes period, you're getting from the lower to the top and back down again. Now, all of the control systems, when you look at the 4-second data, which is not as precise as high-speed data, because it's aliased, you won't get everything, you see that the machines are all hunting. You do see it. So they are hunting against each other. It's an unacceptable situation to be in.
Malta?
In a fast forward 30 years, 100% renewable markets, everything digitally controlled, no large synchronous.
No large rotating machines,
Or maybe, some hydro still. But what is then the importance of frequency control?
Okay. Okay. So this question comes up when I had the young people from AEMO. They said, but we're going to there. And I said, yes, but you're here. We're here now. We've still got 80% synchronous machines. So the question becomes one of, do we want an orderly transition, as our Prime Minister would desire, or a disorderly transition? And I would suggest the way we're controlling will lead us quite quickly within the next 5 years to a disorderly transition in which your utopia 30 years hence will actually be needed now. So I think we have to think carefully. We must understand rotating machines as much as we understand power electronics. And this was a point I was actually going to weave in at the start. I think what's happened is that there's a lot of research focus on the new technology. It's fantastic, it's great. But in order for the new technology to be integrated well with our power system, we have to also understand the old stuff. It's 50 years old. Yes, it's got new controllers on it, but it's still a rotating machine. And we must understand how to control rotating machines in conjunction with the new stuff. So my problem with the way that we're going about some of the new controls, we can do very fast stuff with digital control, right? Okay, so let's travel forward to the time when we've got only hydros on the power system and some synchronous condensers because AE won't want them. And then you've also got the digital control stuff in your solar farms and your fully converted wind turbines and any other fancy tech that comes along, right? If we put only super fast control over here and we have hydros, hydros are inherently limited in their response. Why? Because they're controlling a water column. And a water column of energy has a time constant. And what can happen to a hydro machine very quickly, if you respond over here to a deviation and you fail to properly coordinate all of the controls, you can respond and fix the problem that the hydro thought it had, and the hydro will overspeed because its water column's picking up and it will take off. And you can't slow it down and you can't stop it. So if we don't understand the need to coherently control all elements on the power system, we will cause ourselves problems. So these are the problems that the engineers knew how to fix in the 80s. And I keep saying this, I keep fixing problems that the engineers knew how to fix in the 80s. Cabling is a classic example. Every wind farm in Australia had cabling issues. Why? Because the people shoving them in the ground didn't understand the design and delivery and the accessories and how to do it and all the science of putting together a cable in the ground with a joint. Huh? That technology's been around for, well, since the 80s in XLPE, and yet we've been fixing it again. Right? I'm still having arguments. I think all the solar farms are going to have just as much trouble because of the way they're designing. And look, that's getting personal now, but you know, these are the sorts of issues that are happening. We need to understand the science of every element in our system, and we need to understand how to control it. And we can't just plonk new technology in and do all the fancy shit if we don't understand, sorry about swearing, if you don't understand the old stuff. And yes, we've got new controls on the old stuff, but those controls, are they sensible if they defeat our response to frequency? Like, we can do that now on a large synchronous machine. We can tell it to follow an external signal. So Dylan can come along and tell me, go down, even though frequency needs me to go up. Right? And why do we control frequency tightly in a power system? Because people ask this, oh, we don't need frequency. Because I've heard that. I actually heard it in a Melbourne Uni seminar. About a year ago, somebody, academic at the back, asking that question. Why do we need frequency control? Let's think about it. The frequency measurement is a measurement of health of the system. It is a sensitive balance as to whether we are matching the load. If the frequency deviates, we know we've got to do something to fix it because it's telling us that something's gone wrong. We've lost a load or we've lost a generator. If we have a wide tolerance and we're letting it meander, at some point we're going to have to figure out when it's really bad. But control systems need a reference. We've chucked the reference out. And we said, here, have a control system with no reference, or a reference that's this wide. It doesn't make sense. So primary control is fundamental, and we've got to regain it. And what's going on right now is not going to, we can't ask the demand side response to fix what those big units are doing. Right? Let's go back up to one of those pictures, one of these lovely, I'm finding it first. Let's go back. Okay, one of these. Oh, let's go back up to the bad ones. Look at this. That's terrible, shocking. Let's go back to this one. 33.5 gig of energy doing the wrong thing. Right? You can't have 100 megawatt of demand side response. Let's say the smelter can do something. What's it going to do? It can turn on and it can turn off. It shouldn't do more than that because it's trying to make aluminium. Right? It's trying to make aluminium. We shouldn't be asking our widget makers to do what these guys aren't doing, which they know how to do and they should be doing. I find it ethically irresponsible. Right? I'm serious. From an engineering point of view, I have to call this for what it is. This is a control system that has lost the plot. Okay, next question. Enough of my preaching. Yes.
Last year in the Finkel report, I made a comment in the response to Finkel that if you've added up the senior directors and managers in the regulator, the commission, there's another one there somewhere, isn't there?
Yeah, the Energy
like
Market Commission.
If you there was about 33 or 34, call it, I don't know exactly.
Yeah.
But out of those positions, I think I counted 3 power supply engineers.
Power engineers, yep, that's right. We have de-engineered our system significantly. It is a significant problem to me, and I actually submitted to the Finkel review a couple of points, and he did pick up on a few of them, frequency control being one of them. But it's a very clear point. We've got a problem in power system engineering in the sense that during the 90s, not long after I graduated, because I did graduate late, we dismantled the courses in many cases, and actually it happened globally. So we have a generational sort of gap in power systems engineering. Added to that, when we broke up and privatized the industry, what we forgot is that the industry depends on the input and the mentoring of specialists. Every single element in the electrical system is a science in itself. And what we have lost is those specialists who follow the older fellas, you know, coming through from the public utilities. Many of the engineers that I depend on are at retirement age, and many of them have actually retired. So a lot of the specialisation that we had, now we're struggling with, and we need people. As I said, I'm challenging everybody to become expert in rotating machine control. Right? If we don't understand rotating machines, how do we actually make the overarching power system response coherent?
Sorry, I should have said the balance of the people were lawyers, economists, accountants.
And policymakers. Correct. And so when you look at the frequency, and I spoke to the AMC about the frequency control problem after their frameworks review, and they said, now what did they call it? There's an access rights law. So because we've allowed the law to be created in a manner that says that your contingency service commences at the boundary of the normal operating band, and everybody's put in these control systems that sort of do that, which basically says, I'm going to wait till I get to 90 before I put my foot on the accelerator. Huh? Then the end result is they're scrambling and they can't figure out how to untangle that mess. Now, inside NEMCO, the NEMCO control would have and should have picked up on the necessary requirement for primary control, but they didn't because they were busy focusing on implementing markets. And they never assumed that governor control would be switched off, because all their working life, governor control was mandatory and analog. You couldn't talk to it. So with the advent of digital control and the internet and the capability to talk to a control system from a remote somewhere and send you a set point and a change of mode, they can now enable and disable themselves in accordance with the market. You could never do that when we created the market in the first place. Do you see how this is a comedy of errors? You know, that there's no one single thing that you can point your hand at and say that's what caused it. But I agree, we have a lack of engineering oversight. And in fact, I think that the Energy Security Board should have been an engineering security board. No, no engineers on that one. Yep, lots of lawyers and regulators. Yeah, it's highly problematic. Yes. One more?
Thank you for your presentation. Other than the point that you made about how we are changing from synchronous to
asynchronous or digital control, or
yeah, I agree with you that the fact that rate of change of frequency is dependent on the governor response and everything. So we eventually need to have some sort of synchronous generators within the grid. But other than that, if you think about the future and where we have lots of asynchronous generators connected, you'll have the batteries play the role.
Correct. Yep. Or you may,
So
yeah, or any other.
That's why you have
storage
to
device.
loosen for the frequency control, have it the range.
Why do you have to loosen it?
Because for batteries to kick in, you have a time delay.
No,
other than that.
No, you don't. No, in fact, batteries can respond faster than a synchronous machine. Am I correct?
No.
Yes, I am.
Sorry,
yeah, I am. They can do it in milliseconds. Did you hear what I said about the inertial? You're talking about the inertial contribution, not the control action.
Yeah.
The inertial action of a generator. Is it any good if you don't put any control action after it?
No.
Right. So why do we talk about inertia from synchronous machines without thinking about what it takes to control that inertia? Because if you fail to control the mechanical input into that synchronous machine, it will continue to slow down. Right? So why do we think that it is suitable to only talk about inertia from synchronous machines and not talk about the control of the inertia with arresting energy that follows its inertial response? Because its inertial response is useless if it fails to increase its mechanical energy to recover its position.
But inertial response inherent. It's not done within the control system.
Yes, that's right. It's an uncontrolled action. It's an uncontrolled action. It's a physical response.
So it doesn't have anything to do with setting up deadbands or anything.
But the mechanical energy into the machine to arrest it slowing down is a control action. So there's inertial response, arresting energy, right? And the frequency response overall, which is the sum of the two, the inertial action and the control action. Because if you don't understand frequency response with the two hand in hand, you're forgetting one fundamental point.
So if you're talking about before frequency nadir, you're wrong. But after that,
No. What creates the frequency nadir?
Your generation.
What creates on a synchronous machine, let's just assume you've only got one. You get an event, right? So you've got an imbalance, right? What will arrest the energy or create the nadir?
Rotating momentum.
There's rotating and momentum, but if you leave an electrical imbalance between the mechanical power and the electrical power, you will continue to slow down. At some point, only when the electrical power and the mechanical power are balanced will you stop. So if you leave the imbalance there and no response from the mechanical stuff, you will continue to slow down until you reach that balance point. Guess what? That could be below 47 hertz. And in which case, lights out, right? So please, when you're contemplating inertia, you must understand that the mechanical response into the machine to arrest the slowing down that is happening because we're sucking energy out of it physically, we have to do something. And it's no point getting somebody else to do it somewhere if this machine is the biggest machine on the power system. Because it's irresponsible of that machine to not do something if it wants to keep the lights on.
Okay, I think we might have to leave it there, I'm afraid. We're a little bit running over time.
Oh, I get a little bit, you know.
If it's okay.
Yeah, sure.
Perhaps Kate might stick around if there's more.
Oh, coffee. Just give me coffee. I'll be here.
More questions afterwards. But yeah, thanks again for coming along. Our next seminar next week, same time, same place, is with Robin Eckersley from the School of Geography. She's going to be talking about the sort of changing roles of China and US in the sort of global negotiation space around climate policy in UNFCCC kind of negotiations. And then I think on the 3rd of September, we are having another, or we were co-hosting another event with Beyond Zero Emissions around electrification of industrial processes. And that will be in the chemistry building, and I think in the evening. But if you have a look on our website, you'll be able to find out more details. Thanks.
Probably the highlight.
This one is Holly's Untitled.